Okay, this is a problem from Fabrication Engineering at the micro and nanoscale by Stephen A. Campbell, and this is example 3.2 from chapter 3 of the book. And so the example says, a wafer is heated to 1000 degrees Celsius and exposed to a high concentration source of arsenic. After 5 minutes, the wafer is removed from this source, the surface is sealed, and the wafer is annealed at 1200 degrees Celsius for 6 hours. Assume intrinsic diffusion. First, find A, Q sub T, the dose, B, the final profile, and C, the junction depth if the wafer initially was doped with a p-type of 1 times 10 to the 15th per cubic centimeter. Okay, so let's take a look at this problem, and I'm going to find the correct answers for this example. So in the first case, to get started with, we have the diffusion coefficient is equal to d0 plus n over n SPI times d minus. And each of these can be expanded. So first of all, looking at table 3.2, we see that we have to include both the initial diffusion coefficient and the -1 diffusion coefficient in the case of arsenic in silicon. Okay, and so I have to figure out these two diffusion coefficients. So the first one, or I have to include those two terms, is d0 times Euler's constant E to the E sub A activation energy 0 over KT value plus again n over n sub I times the diffusion coefficient d0 minus, these are both going to be from the table, e to the minus E sub A minus over KT. Okay, so from the table, table 3.2, we can find that d00 is equal to 0.066, and d0 minus is equal to 12. Activation energy E sub A, or E0 sub A, equals 3.44, and the other activation for the -1 charge EA minus is equal to 4.05. Okay, and the we also may remember that the Boltzmann's constant is equal to 8.617 times 10 to the -5 electron volts per Kelvin. Okay, and that can be found in the back of the book where the physical constants are. Okay, so first thing we might want to do is calculate a couple of KT values. One for I'll calculate a KT value for 1100 degrees and another one for 1200 degrees, and then we can plug those both in here and get the diffusion coefficients for both of those cases. So the KT, if I take K times temperature, remember temperature has to be in Kelvin, so I end up with 8.617 times 10 to the -5 electron volts per K times 1100 degrees Celsius plus 273.15 to convert to Kelvin. So going to calculator for this, I can enter 8.617 e to the -5 times parentheses 1100 plus 273.15 3.15 close parentheses, and that is equal to, I'm going to write that down, 0.11832. 0.11832, and since this was Kelvin, the units cancel, and we're left with, that is electron volts. Okay, going to the other value, kT, this was for 1100 degrees C. If we go to 1200 degrees C, we have the same thing, 8.617 times 10 to the minus 5 electron volts per K times, in this case, 1200 plus 273.15. And I'm not going to do the calculator on this one, but you can check it on your own just to verify that I did it correctly, and that is 0.12691 electron volts. Okay, so given those two values, I can now the one thing I have left is this n over n sub I, so I have to figure that out. Now it turns out that n equals nd over 2 plus the square root of nd over 2, and this is squared, plus n sub I squared. Okay, now just like at the previous example 3.1, it turns out that we're assuming intrinsic, it says to assume intrinsic diffusion, which means that nd is very small compared to ni. So in that case, this term cancels, these two terms disappear, and we end up with n equals to the square root of n sub I squared, well, but that's just n sub I, so our n is equal to our n sub I. So if we look back up at this equation, this term will be n sub I over n sub I, and so that's going to come out to be 1, so that this term here is just going to disappear, basically. So, or it's times 1, which makes it go away. Alright, so now I can plug in my numbers, and so let's take a look at that. So I have my overall diffusion coefficient is, in the first case, is going to equal 0.066 times Euler's constant e to the minus 3.44 divided by 0.11834 plus 1 n sub I over n sub I over n sub I, okay, times 12 times e to the minus 4.05 divided by 0.11834. Okay, so let's feed that to the calculator and see what it gives us. Oops, I'm going to do this one. Let's do this. Okay, so I have 0.066 times, I have to do inverse E, and I'm going to put some parentheses on this, parentheses, minus 3.44 divided by 0.11834, close parentheses, plus 1 times 12 times, got to do shift again, e to the parentheses minus 4.05 divided by 0.11834, close parentheses, enter, and So that comes, so I'm going to write that down, and let's do that. That came out to be, so my D at 1100 degrees came out to be 3.1983. I'm carrying through quite a few decimal places on this just to avoid losing accuracy on my way through the calculation. And the units on that are centimeters squared per second, which we're left off here, but the units on each of these coefficients is centimeters squared per second. This is also centimeters squared per second from the table, so our final units are still centimeters squared per second. Okay, doing the same calculation for this at 1200 degrees, the only thing that changes is the KT value here is now using this KT value, 0.126941 electron volts, and if I go through the math on that, you should come up with approximately 2.8 times 10 to the minus 13, and I forgot to record all my decimal points on that one, so we'll just leave it at that. So that's the one so that's the diffusion coefficient at 1200 degrees C. So those are the two values. Now you'll notice that in the first case, yes, okay. So now we have to go and check to make sure that our if the square root of dt is much at the initial dt, one at 1100 degrees, see, and this was, remember, for only 5 minutes, if that's much less than the square root of dt at 1200 degrees, and remember this was for 6 hours, quite a bit longer, 6 hours. If that condition is true, then we can use the approximation formula for dose. Okay, so so we need to check that first, and so that's the next thing that's done in the example. So we need to figure out these two values. So the square root of dt at 1100 degrees C is equal to the square root of the dose, which is 3.1983 times 10 to the minus 14 centimeters squared per second, times, and this was 5 minutes, but you have to convert to seconds to get the seconds to cancel, so that's 60, there's 60 seconds in 1 minute, and so I have to multiply by 60, and so that'll be the same as 300. So let's take a look at the calculator for that one. And so I have I have to do square root first, parentheses, 3.1983 e to the minus 14 times 5 times 60, close parentheses, enter. And so I have, I'm going to write this down, 3.09 times 10 to the minus 6, and so let's take a look at that. So the square root of dt at 1100 degrees C is equal to 3.0976 times 10 to the minus 6, and the units are square root of centimeter squared is centimeters, so that many centimeters. Now first of all, that doesn't match the answer in the book, which is 0.092 microns. If I do convert to microns, remember that there's 10 to the 4th microns per centimeter. Remember, it's 10 to the 6th microns in a meter, but since a centimeter is 100 times smaller, there's only 10 to the 4th microns per centimeter, which if I multiply that by 10 to the 4th, I can just add 4 to this, so that's 10 to the minus 2, or as it's written in the book, 0.0, move the decimal place over 2 places, so it's 0.0300976 microns. Okay, and that is a weird number, but if I look at this, if I square that, 0.03 squared, so let's take a look at that. If I were to square this value, it comes out to be, well, pretty close, 0.0 to 0.092. So I'm not sure where the 0.092 error came into this, but that seems to be an erroneous value. Okay? Just check my time, and I'm over.